I wanted to first point out that in the README file for the GitHub repo where all the tutorials at, we've added this list or little table of content that specifies each of the presentations or tutorials with links to the specific notebooks, just to make it easier for you to remember or navigate rather than trying to remember the names. Yeah, so you can refer to that. Okay, so back to Jupyter Notebook. We will open the mashup water budget notebook. So you go to the left thing. Hopefully this font size is fine. Let me know if it isn't. But I will close this too to get more real estate. Okay, so I'm going to bring together lots of different elements that were presented by Ifan and Stephen into what is hopefully a coherent and realistic analysis that you might do. The objective is learning, but it's more about a storyline here. That's constructing a monthly sub-watershed or watershed scale budget for the same upper Yakima watershed that Ifan focused on, using geospatial watershed layers and a wide variety of water data that is relevant to this storyline, including remote sensing products, multi-source climate products, river discharge at a gauge near the watershed outlet. I'm going to skip through this, or the goals, or the sequence of steps, because I'll go through that. But you can take a look at that, which packages I'll be focusing on for each of those tasks, and what the task entail. For example, initially, I'm going to use a new package for bringing in US hydrography geospatial data sets for watersheds, instead of relying on a preloaded shapefiles. But to summarize this, you could say that at the end of this tutorial, you should be able to mix data types with abandon, from multi-dimensional gridded data to geospatial vector layers to point time series. Or at least the elements will be there for you to be able to do some elements of that. I've added a lot here, so I wanted to make sure that none of you feel inadequate if you feel that you're not following every single element. The idea is that with this and all tutorials, really, these are resources you can go back to and pick, either look at them again or pick out elements that you feel you might use for your project, or that you just want to learn at depth. So don't worry about the fact that there's a lot. Okay, so back to the upper Yakima. That's a Huck 8 with that. What I'll do is focus on its sub-watershed. It's a primary breakup into sub-watershed. So that would be Huck 10. You'll see the UI shorthand quite a bit in my variables. That refers to the upper Yakima. I think both Ifan and Bart already alluded to the watershed boundary data set from USGS for the US and HUTS. One important thing about HUTs that I'll refer to is that the codes built on one another. So the 2-level HUC, it's a 2-digit, 1-8 for California in this example. The next level in detail, the HUC 4, it's 1809, and so on. So other digits added are the end. And that scheme can be used for analysis, if you will, knowing that scheme. I wanted to point out that for global applications, hydrobasins is probably the best, or one of the best data sets available. I don't think it includes the very high latitudes, although that may have changed. And it's based on these great global data sets called Hydrosheds that starts out with the digital elevation model. Hydrobasins also uses a hierarchical watershed coding scheme. It is different from the one used in the US with HUCs. It's called the FASTER system. It is widely used across the world. But there's an intelligent scheme that allows you to make inferences about hierarchies and locations. I wrote a tutorial for Waterhackweek that you can go see. It goes a lot into GeoPandas also, that uses a hydrobasin data set. Okay, so instead of manually downloading HUC shape files and then placing them in the GitHub repo and then reading files, I wanted to do everything from fully remote access. And turns out that there is a fairly new package developed by a grad student at the University of Houston called Hydrodata. It's really a suite of packages. All it does, one of the key things that it does is provide access, remote access to data services provided by others, especially USGS. The package PyNHD, the National Hydrography data set, has all the elements for this. So I provided background on that and on HUCs. We know the, oh, I forgot that I'm going to be running this. Okay. And I'm going to load files. I put all those specific packages, the loading or importing of them here, just because they're only used in this section. I know the HUC8 code because EFON already had it. What we're going to do now is I'm going to start with the HUC8 code. At this data service from USGS available via Hydrodata, it turns out it doesn't provide HUC10s directly. That's a shame, but that's the reality, I guess, of relying on what data is available. It provides HUC8s and HUC12s. So what I'm going to do is load the HUC12s, in other words, the smaller watersheds, and do what's called in GIS a dissolve back to HUC10. So I created this convenience function to enable a filter to be passed to the service for HUC12s. In other words, to select a list of HUC12s based on them having the HUC8 code. The Hydrodata package is in very active development. These features that are all in this complex code will go away because I've already contributed this code to the developer, and even by now there's a new release that so that I wouldn't need a special function for this. It's all taken care of. So that's the beauty of open source. Okay, so here I just set up the function to be reused later. Water data is a class in PyNHD. I'm specifying that I'm going to interact with the HUC12 layer, a spatial layer, and I have to specify the CRS, the coordinated reference system that it's in. There's some messiness here about how USGS has set up projections and what projections, but that's life. We can get access to what attributes are available on that spatial layer. And now I'm going to use that function that I defined where I pass this, if you're familiar with SQL, this is a lot like SQL, this filter scheme. HUC12 is the name of the attribute. And I use the code with this wildcard that says anything that starts with the HUC8 code and the other digits can be anything. So I'm getting all the HUC12s that are in the desired HUC8. And I get it back as a geodata frame, which is really convenient. I haven't downloaded anything. I now have a super convenient geodata frame of exactly what I wanted, which is great. No download and exactly in the format that is perfect. I'm still at a HUC12 because that's what I was asking for right now. But in order to create a HUC10, in other words, the more aggregated one from a HUC10, I use the dissolve function. Again, if you're familiar with GIS, you'll recognize that. And the structure of the HUC codes. So this, you can see here that I'm working on the geodata frame, which is just like a data frame, taking the HUC12 attribute and pulling out the first 10 digits to create a new attribute, HUC10. And then I apply the dissolve operation on a geodata frame on just those columns, applied on this new HUC10 attribute, and the aggregation function on numerical attributes is the sum. Okay, I'm gonna run this. And the length here tells us how many features or rows there are. There are 7 rows or watersheds. Let's see what that looks like. That's what it is. It's just 2 attributes plus a geometry, as opposed to all of those, which drop out because they don't make sense when you aggregate to larger watersheds. Okay, a nice thing about GeoPandas, just like with pandas and XArrays, that it provides these really convenient and easy plotting functions. So I just add the plot and I get a simple but useful map, and you can see the watershed boundaries faintly. You could customize this, but for a quick view, this is great. GeoPandas also provides great features for extracting information about the geometries. In this case, the total bounds, it's a bounding box that covers basically everything, the min and max, lat and long. And I'm going to reuse that later. I'm going to save it and as a geoseries, a GeoPandas geoseries, basically that rectangle, and reuse it later to clip or make requests on multidimensional gridded data. And as part of that saving of those dimensions, I'm going to turn that those total bounds from that geoseries into these slices, the longitude slice and latitude slice that I'll reuse later. So I just do it here, save it for reuse. Let's get a better sense of what this looks like, because that was a very convenient plot, but also kind of ugly. This is using Contextly, an add-on that allows you to bring in any, on top of Matplotlib, any nice base map, just to get a quick geographical sense. So I put the boundary here, and that base map, and the HUC10 watershed boundaries. Note that there are this black smudges. They're effectively holes in the polygons. And I don't know if it's in the original data or if it was a result of the dissolve operation, but often called sliver polygons, but they won't affect anything we're doing. Now that map is great, but I rather use something more interactive. So I'm going to use Folium, the same what GeoFind already used. And I'm going to define what background I want. GeoJSON is the way to, I think GeoFind used it, the way to bring in a geodata frame with vectors, especially polygons or lines. So I'm going to add the bounding box, as well as the HUC10 boundaries. But I'm also going to add a couple of things that are defined here. A tooltip, so you can see, again, for convenience, you can see quickly which HUC10 it is, but also a pop-up. So I can see a bit more, not just the HUC10, but the watershed area. So attributes that are pulled in from the geodata frame. All right. I'm going to define here for use throughout the notebook that I'm going to focus on the year 2016. So I'm going to define date start and date end. Again, that's rather than having to define it over and over. Stephen already addressed the OpenDAP data service that XRA takes advantage of. And that's what I'll be doing for the most part here. We'll be access spatial, temporal, and multidimensional gridded data from 3 completely disparate and unrelated data services for the Upper Yakima for 2016. And then we'll reprocess them to be consistent so that we can do common operations. Okay, we'll start with water data. With precipitation. So what is a water balance? It's typically precipitation, water coming down, evapotranspiration, and discharge. Those are the 3 key fluxes. So we'll start with the beginning, precipitation. It's DAMET, so I won't go into details but about DAMET because Stephen already did. But I will remind ourselves that we are accessing a remote data source that is large. Stephen emphasized this, not only in the dimensions in time, X and Y, but also in the number of variables. So you should be careful when you post a request of what it is you're doing and what's going to happen at every step. Because you don't want to be, if you're only going to use a small subset of data, you don't want to download or try to download everything all at once and then process it in memory. It's possible that the server will tell you, I can't do that, that's too much, or your computer will tell you that. Also, as Stephen mentioned, that this is in Lambert conformal conic projection, not latitude and longitude, but I need to have a common set, I need to bring everything to a consistent single projection. So I'll need to reproject it, and I chose to reproject it to lat and long to do the mashups. Okay, so here's the same thing Stephen had to access the data set. To do the reprojection, I need to look at the projection information that's embedded in this data. And I need to run things, not just, okay. And you can see this attribute here, Lambert conical. It has information that defines the projection. You can see also things like in precip, there is this grid mapping attribute, Lambert conformal conic. So you can see that there's a referencing system here. For each variable, it says the grid mapping, it is that one, and it's defined here. That is part of what is called the CF conventions in for NetCDF data. That is the most widely used and important set of conventions for metadata and for data structures. So we take advantage of that knowledge. What we'll do now is take our bounding box of the upper Yakima that was in Land Long and now transform it to Lambert conic. This is what Stephen did to get the CRS based on that information. In other words, it's going to read the information from the data set from that variable and transform it into a projection object, if you will, that looks like that. And now I can take my bounding box geoseries that I had that was in lat and long and use GeoPandas functionality to convert it to this new Lambert conformal conic, where again, I didn't hardwire anything. I just read the information from the NetCDF file, knowing that, or after having checked that it complies with the CF convention, so it'll work. We don't have to fine tune it dramatically. I'm extracting a bounding box here. Okay, so I'm still not there. I've just defined my bounding box in Lambert. Now I'm going to define the subsetting scheme. Remember that this operation, opening the data set, doesn't actually load data. It's just metadata. It's what's called lazy loading. I need to be thinking deliberately about what it is I'm doing at every step so that I don't bring this system to a crawl. So I'm defining here a selection that doesn't actually bring in the data. It just defines what's going to be done. Here's the time slice, the X slice, the Y slice. And the X and Y is passed in the Lambert conical because that minimizes, that makes the request faster. And this is what the output will look like once I actually make the request. You can see that it's much smaller. It's just 1 year, 365 days, and well, much smaller. And I also selected only precipitation. So this is a data array. I'm throwing out things that I don't need. Okay, now I'm actually going to do it, to do the reprojection on this subset that I've defined but not executed yet. Now, this function that I've set here is hairy. This is where the magic happens for reprojection on a data array. You pass it a data array and the name of the grid mapping and what conversion you want. And we use this library called Rio XArray that sits on top of XArray. First, we clean up the or improve the projection information that's embedded in that data set so that we can do the reprojection unambiguously. Then we perform the reprojection, Rio reproject. And then we do sort of more cleanup of the output, the reprojected data set, that to adhere to CF convention expectations and a few other issues. And then we bring back attributes. When you do operations on data arrays, attributes are often lost. So I put them back in and it returns an XArray data set. So anyways, lots of details here, hard to follow. It took me a while. I'd never used Rio XArray. It took me a while to figure it out. And in the end, I can just use the function. Okay. So this function now is the one that is actually going out and issuing this subset request for a small set of data and reprojecting at the same time. So this is the one that is actually doing all the work as opposed to defining what it is I'm going to do. And now I've got the data in memory. I was curious to see, just double checking that cell sizes made sense. So don't need to go into that, but that's what it looks like. But of course, I want to map it. I have no confidence that this is correct if I can't see it. So I'm using matplotlib, adding the Hug10 boundaries as a reference point, and it looks good, and it's in lat and long. Woohoo! Because of the reprojection step, you can see though that there is extra space, and that you can actually clip it a little further in lat long space. So I'm going to do that so that the data set is smaller. And I use the RioXarray clip function using the geometry in lat long space. And then plot the same thing. See, now it's actually, I forgot that it's not just, it didn't just clip geographically, but it also threw out data that we're not going to use outside of the watersheds. So we got a nice and lean data set. Okay, done with that. Well, done at this stage. The next data set is really nice and clean. It's the cleanest and most compliant data set of the three that I'm going to address. It's evapotranspiration from this, the simplified surface energy balance, actually evapotranspiration for the conterminous US. USGS provides it. The resolution I'm going to access is monthly. Again, it's an OpenDAP endpoint from a thread server. And I'm just going to run through them because I'm basically doing the same thing as before, and but much simpler. I'm just adding the projection information. I don't need to reproject. I don't need to deal. There's no mess to deal with, and I'm just going to plot it. Yes.
Emilio, after this, if there's a good point to break for a second, let me know.
It is coming very soon. So this is the MODIS-derived, remote sensing derived, same thing we had before, except for evapotranspiration. The other data was daily, this is monthly. So we're getting there. The next data set, and I'll stop after doing the processing of this one, is what's called water storage from GRACE. GRACE is a pretty neat and unique satellite that measures gravity, basically. As it's going over, it measures how gravity changes. And then there's processing involved that separates changes in gravity from time to time to water, for example, and the combination of liquid water and groundwater and ice. So one of the products, it's water storage. It is very coarse in spatial resolutions. That's the downside. It is monthly, half-degree cells, but it's pretty unique. There's nothing like it. So I'm gonna open, same thing, open data set, take a quick look at some of the features. There's a messiness here, and that is not unusual. Every other data is, longitude is in -180 to 180, which is probably the most common form. This is 0 to 360. So in order to bring it all into a consistent form, first I had to realize that, and I could see it here, 0 to 360, darn. Then I had to Google how to do this, and that this implements that transformation of the longitude. Well, this implements the query, actually, the same thing. And then the transformation of longitude, and now we have the clip data set, and I'm going to plot it. And you can see how extremely coarse it is. Basically, the whole upper Yakima is one cell. And this is exactly the point for questions.
All right. Oh, perfect. You actually even have a placeholder for it. Excellent.
For myself.
No, that's great. I think there was at least one question that we had, like very early on in the presentation, when you defined the function in like cell 4 or something like that. You actually already specify the coordinate reference system, the CRS information. And the question is, how do you actually find out what that is, what that string should be?
In this case, I am making, I won't answer that fully because here I am interacting with a remote service and what projections the data is available in. And it turns out, because this is from what's called the USGS Water Data Lab, as opposed to water data, really robust and permanent and well-documented service, it turns out they had some projection messiness, and I went back and forth with the developers. So I had to figure this out the hard way, what would work. Normally though, for this particular service, normally a geodata frame has, when you read a shapefile, for example, if it has a projection file, it'll have a projection. Let me show you an example. Okay, here we go. So part of a geodata frame is a projection, and it's got the CRS attribute, and there it is. And that's what gets used. So it's metadata that is stored internally. And then you use that for reprojection, for example. When I had a step that was geodata frame to CRS, you have to know the from in order to apply it to. Yeah, but in this function, it's there is no magic. I had to do it the hard way. I have to look at the outcomes, and there's just some messiness in there.
And so what about the next line where you have the HUC 12 and then it's 900913?
I looked at the data service to see what was there. Yeah.
So no magic, just elbow grease, basically.
Pretty much, pretty much. But in
Yeah,
principle, if you were going to do this over and over, and you were going to work with that data service, this is something that you can automate. You can write the code that would know where to look, and then you don't have to hard code this.
Okay, perfect.
Yeah, there was a similar question about like, how did we know the y-axis is reversed in the day met, or how do you know to switch like from -180 to 180 from 0 to 360?
There are wonderful resources for data access, and the ability to have this X-array metadata is just amazing. As Bart was saying, back when we were kids, it was so much messier. But it's still not a perfect world. CF convention, for example, is fantastic, but it has some leeway, and not every data set adheres 100% to it. So my practice is that when I first read the data, I take a hard look to see if anything that just seems abnormal, or after I try to do something, it breaks, it doesn't work. So I figure out, why didn't it work? So for example, the -180 to 180, I don't think I spotted it from the start. It's when I started using it, I realized, oh no. And then you go, that's a common problem. Okay, how do I do this? I can't remember, I'll Google it. And that's what I did. You Google it and you often land on Stack Overflow for answers.
Yeah, and I think actually that's a really good point, right? Like when you get data from a new source, make sure you look at it, like plot it and look at it. It isn't always what you think it is, or organized the way you think it is. And it wouldn't be the first time that somebody used a really high level kind of analysis function and calculated the mean over something that wasn't over what they thought it was. So looking at the data and kind of managing this data remains a large part of any project. So we don't have any, we don't have any other questions at the moment. So let's keep continuing, or let's continue, I guess.
Yep.
Anybody, just keep entering questions in the tutorial channel, and we'll kind of manage them in real time. All right.
Okay, so just to review where we are, we've defined our geospatial area. We've got our HUC-10 watersheds in a wonderful GeoPandas geodata frame. We've got bounding boxes. We've already read into memory the 3 multidimensional data sets at their original resolutions, daily versus monthly, whatever spatial resolution they had, but we've got them ready to go. And remember that they came from vastly different sources, satellite, gravity satellite, MODIS, processed with the model, and so on. What we're going to do now is apply a common scheme for generating HUC-10 sub-watershed level averages for each of this into monthly, our common monthly resolution that is our target for the water budget. We'll use this package called region mask to take our geodata frame and define what it calls regions, and then turn that into rasterized mask that we apply on each of the data sets. Region mask has a very nice feature from GeoPandas. So it takes a geodata frame to create its own object regions, and there they are. I passed it the HUC-10 attribute because that's what's most useful. But we can also visualize them. It's got a really nice, convenient mechanism for plotting them. So you can see it's the same watersheds, but it puts those labels, the region labels on top. So it's pretty convenient. Okay, now I'm going to define another function where I stuff a lot of the complexity. This function, and I've try documenting it. The idea is that for some of your projects, you may find these functions useful. It takes a region and then it converts it into a mask. In other words, a gridded mask from the regions based on the resolution of the data set that you pass it to, the X-array data set. Because we're dealing lat long, it ideally should define the fact that cells, the area of cells vary with latitude. So we have this weighing by latitude, even though because the watershed is fairly small, it's probably not really needed. And then we apply the X-array data set weighting function by area on that mask and apply a mean function. And this just says that we're going to average over latitude and longitude, and we're going to be left with only the time dimension. And I should back out and say that the one caveat or limitation for region mask that I find is that it's hardwired to only work with data in lat long. In other words, you can't use it for data in any other projection, which is a real shame. Hopefully at some point it'll be improved, or we can improve it. Anyways, so here got the data set that is area weighted and a mean that yields time series. And now we just clean it up. We give it a name. We port the attributes that we lost, the variable attributes, the name and the units, and we clean it up further. Okay, now we're going to apply this to every one of those three variables that we have. We apply this function. We pass it the geodata frame, the data set, the upper Yakima X-array data set we constructed, the variable we want, and so on. And this should be, oh no, what did I do? Oh, I didn't run this, okay. And this should be fast now because we got the data in memory and it's fairly small data at this point. This is what the data arrays look like. There's the regions, abbreviations for the regions, and the attributes of the variable. We're doing precipitation right now. Remember that that was daily resolution, but we're going to operate in monthly. Our final output is monthly. So we need to resample or sum to monthly. And we'll use the resample function, just like Stephen did, and sum the daily values. And then we tweak the variable attributes because now they are monthly. The units are differing now. And I plot it. And just for comparison, this is the original daily. So these are the time series for each of the Huck-10 watersheds. So those are the watersheds. This is the monthly values and the daily values. Again, we started with this and went to this. You can see that there's actually a substantial difference. There's a bunch of watersheds that are quite arid. Even during winter, precipitation doesn't go very high, and there are others that that do. I was a bit surprised to find so much difference, so that was good. Now I'm going to do it for evapotranspiration. Again, I reused the same function, but I passed the same geodata, or regions rather, but now I passed it the evapotranspiration X-array data set, its variable, and so on. And now I take a quick look. Same thing, same scheme that I'm using for the other one. This was originally monthly, so there's no conversion from daily to monthly. And again, you can see dramatic differences between some watersheds where evapotranspiration remains low even in summer because there's just very little water in there. And it's also amazing. My PhD research and the bulk of my hydrological hands-on experiences in the tropics, where there's always plenty of sunlight. It's just odd for me to see that, but not surprising, but odd that there are periods of the year where evapotranspiration, at least according to this data set, is practically zero. That's just weird. But anyways, it was fun seeing what a dramatic seasonal variability there is, and that there are also others where there isn't. Okay, so now we just need water storage. Same thing. It's already monthly, so don't need to do anything. I'm looking at the data array because it turns out that I noticed that there are only 9 time steps. There should be 12. But it turns out this data has gaps. Oh, and the units were centimeters. I'm going to convert to millimeters because that's my common unit. And rename the units. And that's what this looks like. The plot, that's what it looks like now. Even though there are multiple lines, there's a single line, and that's because they're all on top of each other. Because remember those huge pixels? There is no distinction across sub-watersheds. It's all the same. So like I said, there are gaps in this data set. So we don't have 12 values, we have 9. And that's just the reality of dealing with data. Okay, let's look at them together. Now that we've got everything in a Huck 10 level monthly time series, we can start comparing them. Aha, nice. I put them on common axis. All right, we can start looking at patterns here, but I need to move on. Now I'm going to calculate the whole watershed Upper Yakima water budget, the final goal. So I'm starting with sub-watershed level time series. And calculate a watershed-wide time series. To do that, I need to do area weighing. In other words, the relative area of each sub-watershed compared to the total area of the watershed. And that's what this is doing. And I create another convenience function to do this. There's the weighing, a data array that defines the, no, I forget what this is. Where is my area weight? I think I may be reusing this. This looks like it's exactly this. And I forgot to add that variable directly. So I'm recalculating that. And then I do the same cleanups. Bring attributes. Oh, and I convert from X-array into a data frame because now I'm no longer dealing with multidimensional data. I've simplified everything to a time series at one point. And then I get rid of the year part of the dates and turn it into just month because that's all it is. Okay, so that's just the definition of the function that we're going to apply to these 3 data sets that were originally from fundamentally different sources with fundamentally different characteristics. But I've got it now all normalized to this, which is what I wanted for the whole Upper Yakima. For precipitation, 12 months, the values, and they're all in millimeters, because that's the common units. For evapotranspiration, same thing. I'm not going to print it out. Water storage, same thing. And you'll see here that it's missing like 9 in September and October. Okay, I'm getting there. All I need to read now is the USGS NWIS data to find the station, discharge station near the mouth to complete my water balance calculation. I could read USGS discharge data from Olmo, but it turns out that this Hydrodata package has a very convenient feature for USGS data. It's only daily scale data, but for my purposes, that's perfect. I don't need hourly data. So I'm going to use this feature from Hydrodata Interactive Map, which creates a volume map, and I'm going to add to it, add my Huck 10 boundaries. And you'll see why I like it. I've got a volume map, so it's interactive. Same things I saw before, it's clickable. But what Hydrodata added is it queried the NWIS for all the discharge stations in that bounding box. So I know the mouth is around here. It turns out that, oh, and it provides really nice set of attributes about the station that is really convenient. I went near the mouth, which happens to be here, and it turns out that the data there is old. It ends in 1990. Unfortunately. And so I browsed around and found that the closest gauge near the mouth is this one. So that's the one I'm going with. It turns out that much of the downstream area below it is pretty arid. I'm using this feature of Hydrodata called NWIS, or this class, specify the station code that I got from clicking around. In other words, I clicked here, and there's the station number or site number. Okay, then I used another convenience function from Hydrodata, get streamflow. It's going to do a bunch of things. I specified the date range, the 2016. I'm going to tell it to do this, instead of giving me discharge, in other words, volume over time, it's going to normalize by the area of the contributing area to that gauge to give me millimeters per day, because that's how I'm comparing all the elements of the water budget in depth over time. Okay, now I can see what that looks like. And there it is, a simple data frame with just date and the values. I'm going to clean this up a little bit so that it looks exactly like all the other ones I have. And plus, going from daily to monthly. So resample now in pandas, but resampling in pandas looks pretty much the same as in Xarray. Resampling and summing. Okay, so all I did here is go from daily, summing to monthly, but I also changed these names. Instead of that, which doesn't tell me anything, I called it discharge. And instead of daytime, I went to my standardized month number because I don't care about the year at this point. Okay, at this point, I just use standard pandas concatenation of this 4 different little pandas data frames, bring them all, slap them all together. And ta-da, there is my water budget, monthly water budget. We got precipitation from DayMed, evapotranspiration from MODIS derived product, discharge from NWIS, and liquid water equivalent or water storage storage thickness from GRACE. Let's see what that looks like. Oh, before doing that, I'm also curious to compare GRACE water storage to the more conventional difference between precipitation minus evapotranspiration minus discharge. Okay, so I'm going to plot it all together. So I created this new delta variable within the pandas data frame by doing the straightforward subtraction. So first, this messy plot is, and the units didn't come through, sorry. It's all the, everything in that data frame. You can see that I just specified the data frame and then plot. So precipitation is blue, again, for the whole upper Yakima. There it is. Evapotranspiration for the whole upper Yakima. There it is. Discharge is green. That's from our NWIS gauge that is not quite at the mouth. And I didn't scale to the whole watershed area, but you know, I'm not publishing this yet. And then liquid water thickness or the water storage, see how it's gappy, but you can see that it goes like this. And then the delta, it's a purple. And I was really curious to see whether there's any relationship whatsoever between the simple budget delta and GRACE, because I had never worked with GRACE. So I plotted the two. And I don't know, but that's, I think that's for such vastly different sources going into this, that looks linear, close to 1. I didn't calculate whether that was a slope of 1, but it's close. Sure, the error is somewhat high, but I find this amazing that the water storage change at that coarse resolution from GRACE could be what I would consider such a nice match to this delta calculated from these vastly different sources. So here I am. That's what I wanted to do. And yeah,